Hello, it's Keith here, and this is lesson 10 in the platform-specific series of my 68,000 programming tutorials. We've been looking at joysticks on a lot of different systems recently, and this time it's the turn of the Sinclair QL. But you'll see that this lesson isn't called joystick reading, it's called cursor reading. The reason for that is that basically the Sinclair QL can't have a joystick. I think there is like an external add-on board that gives it the joystick support, but internally it has no joystick. So we're going to be reading in from the keyboard, and we're going to be using that to simulate a joystick. So what keys are we going to use? Well, the Sinclair QL works relatively similarly to most 8-bit keyboards in that it uses a membrane and that you've got rows you read in from a row, and each bit represents a key on that row. So quite conveniently, we've got a perfect single row that we can read in, and we can use that as a joystick. So we're going to use row 1 here, and this gives us up, down, left and right, which are obviously the basic ones we need. Enter and space, which will probably make some quite nice fire buttons. And we've even got the slash here, which we're going to use as a third optional fire button. And finally, we've got escape. We'll use that as our start button. So we can just read in a single line, and we can use that to actually emulate a joystick quite nicely. Very straightforward, and of course, we've got no key clash. Now, if you're not familiar with key clash is a bit of a glitch within these membrane keyboards. And what happens is, because of the way the keyboard is laid out, if you have 3 buttons pressed down simultaneously, for example A, H and 6, if the player presses those 3 down, the wiring will actually represent that E is also pressed down at the same time. And it's not actually possible to tell which 3 buttons were really pressed down. Now, this isn't going to be a problem for us today because we're only reading in a single line, but if you were trying to emulate 2 joysticks, or if you were trying to emulate lots of fire buttons, that could be something you do have to consider, and you have to carefully select your buttons to make sure that's not going to become a problem for you. Anyway, today, because the Sinclair QL doesn't have a single joystick, we're not going to try and emulate 2 joysticks, so we're just going to pretend we've got 1 joystick for today. How do we actually read in from the keyboard? Well, unfortunately, much as I love to avoid using the firmware, in this case I don't think we've got any choice. I believe that the QL actually has a separate processor which is connected to the keyboard, and you have to negotiate with that processor to get the data from the keyboard. So we're going to be using the firmware, and we're going to be using a trap. So we're going to be using trap 1. And this is quite a complex command, unfortunately, so we're going to be using this sort of template for controlling it. We're going to have a look at it in a moment, but basically we're using command 11, and we pass a pointer to a command here, and this is the exact command we're going to use. Because we're only needing to load in a single row from that keyboard, we don't need to be particularly complex and reconfigure things, so we're just going to load in a single line, and then we're going to process the data from it. So this template will work just fine for us. We will have a look at it in a little bit more detail when we get to the source code. So enough talk, let's actually fire up today's example and see if it can read in our joystick for us. So here's our Sinclair QL. In these tutorials, joystick 1 is OSD 0 and joystick 2 is OSD 1. Now in the case of joystick 2, we don't have a joystick emulated today, so all the bits are just going to be 1. Now when we press a button down, the bits will become 0. So if I press up the up button, you can see bit 0 goes to 0. Down, bit 1 goes to 0. Left, bit 3. Right, bit 4. And then we've got fire button 1, 2, which is space and enter. And then slash should be fire 3. Where is that? There it is. And escape is our start, the bit 7. So you can see here we're reading in from the keyboard just fine and showing these on the screen. And the code you're seeing running today is taken from my Grime 68,000 programming project, so it does work. It made a playable game in that, so it will work for us today. So let's have a look at the actual code that's doing the work today. Well, it's going to be pretty straightforward. We've already looked at the principle of reading in the keys, so then all we're going to need to do is convert them. So firstly, what we're doing is we're loading the effective address of the QL joy command here, and you can see this is a pointer to this memory here, which is a definition of the command. Now, the example code I'm going to be giving you today is going to work as is, and it always will work as is, and I'll explain things to the extent you need to modify the examples for the purpose they're designed. But if you want to really go crazy with things, then unfortunately you need to get this developer guide here, and you need to start to look at the documentation, and I'll warn you, it is not good. It's not good at all. So I can't remember how I got this working. I think in the end I had to cobble together other examples of sound processing and things because I just couldn't make any sense of this. But we're gonna look at it and we'll explain it to the best we can how it works. But if you really want to go into it, this is the code you want to see, and it's mentioning sound because the same processor does the sound and the keyboard. So anyway, let's have a look at that definition here. So the first byte in the command we send is number 0, and this is the command number, and we want command number 9. You can see a 9 here reads in a row of the keyboard, and we pass a 4-bit row number and an 8-bit reply. And unfortunately, this does come down to sort of how we are actually specifying things. Now, firstly, we've got this send option. Now, this is actually split up into bit pairs, and the different combinations of bits define how much data we're actually sending. We're sending a low nibble, so we just need to send the 2 bits as 0, and we're only sending 1 byte here. Again, this is the bit where it gets really confusing. It does sort of explain this here, but as I say, I did not find it clear, so maybe you're smarter than I am, in which case, well done. But as I say, it does explain here how the bits are working compared to the bytes that are being sent, but as I say, I didn't find it very helpful. Really needed some practical examples, if you ask me. So, and then we've got our parameter, and our parameter is just our row number. So in our example, we're reading in row 1, but if you change this to a 0, you'd read in row 0, and if you change this to a 4, you'd read in row 4. And this is how we can actually read in the keyboard. We just keep changing this single byte here, and the rest of the command stays the same, mercifully so, because it's so complicated. Now, the final thing we need to do is specify the length of the reply. This again uses a bit pair, but whereas we were using 0, 0 because we wanted a low nibble here, this time we need to send a 1, 0, and that's because we want 8 bits. Now, as you can see here, the 0, 0 passes a nibble, 0, 1 sends nothing, doesn't make a lot of sense, but 1, 0 is all 8 bits. So we want to get all 8 bits back in this case. And so that's why we're using that here. Very annoying, but that's what we have to do. As I say though, if you're using today's example, you don't need to worry about this, just ignore it. But if you were trying to do clever things with the keyboard, or if you were jumping ahead and starting to play with sound, you do need to make some sense of these kind of commands. So that's what we do here. We load that into A3, and we load hexadecimal 11 into D0, and then we call trap1. Trap1 sends it to the IO CPU, and that returns the result in D1. Now, D1 is the result from our trap, but we're going to use D0 to store the actual result of the buttons, because we need to convert the value in D1 for our purposes into D0. And we're going to do this in a fairly simple way. What we're going to do is we're going to back up D1 into D2, and then we're going to shift the bit that we want out into the extend flag, and then shift that into our D0, which is our result. And we're going to do this 1 bit at a time, and because the bits are in totally the wrong order, we're going to have to kind of shuffle things around quite a lot. So we want up to be bit 0, down to be bit 1, left to be bit 2, right to be bit 3, and then I think space is bit 4, or enter is bit 5, or maybe the other round, and then the slash here is bit 6, and then finally escape is bit 7. So there's really no combination here that makes any sense to us, unfortunately. So we've backed up at the result. We're just going to keep restoring that into D2, shifting the 1 bit out we want, and repeating as required. Now, in some cases, they are consecutive, so rather than restoring D2 a second time, to get bit 6 here after bit 4, we're just going to do a shift of 2, because 4 plus 2 equals 6. So first we want bit 4 from that result, which is the start button escape. Then we want the 6th one, the slash. Then we want the enter, and then we want the space, the right, left, down, and up. And up, I should have filled that in. I've neglected my work there. And up is the 3rd. So there we go. So all we're doing is we're shifting each bit out into D0, and we're shifting them to the left. So the last one that we pushed in is the one that ends up on the far right. Now here's the format of the byte that this function returns. So up is at the far right, then down, then left, then right, fire 1, fire 2, fire 3, and start. So the first one we did was the escape button, which is our start, and the last one we did was up, and that's the opposite order to the way they end up in. Finally, we're setting D1 to just all 1s because we don't want that to function, and if our game is trying to read a second joystick, we don't want it to play up. And then the only last thing we need to do is we need to flip all of the bits in D0, because the way that they are returned by this function is backwards to what we want, because we want a button down to be 0 and a button up to be 1, and that's not the way that it's typically returned. So we just need to change that, and that does everything for us. Finally, you'll see we've got a command called allow joysticks here. This is just a dummy. Some of the systems we're covering need an initialization routine, but the Sinclair QL doesn't. So we've just got a dummy command here to allow the function to be run in a common way on all of our systems. So a bit of a pain there, but we've managed to get around it all right. Of course, we're only supporting a single joystick. You could, of course, read in a second line of this key map, but then you would be at risk of getting key clash. So you've got to decide if you're willing to do that or not. I mean, you could use these function keys, but you are going to be really risking some key clash there. So anyway, I hope you've enjoyed this lesson. We're going to be doing more joysticks next time. Thanks for watching, and goodbye.